All kinds of machines, vehicles, and systems rely on the transmission of force through rotating shafts known as torque. From engines and electric motors to the wheels of a car to turbine blades in an aircraft engine, torque is present in almost every aspect of everyday life and industry. As a result, the measurement of torque is a huge area, with the torque sensor market valued at significantly in excess of $5 billion per year by independent market researchers. There are 4 key types of sensor technology used to detect torque. Strain gauge sensors. This has been the conventional method for measuring rotating torque by using a piezo-resistive strain gauge attached to the rotating shaft. Changes in strain because of torque are recorded as variations in an electric signal. Advantages are relatively low cost and simple application in a low volume like a test lab. Disadvantages of strain gauges include a reliance on torsional strain inhibits their application to shafts of arbitrary torsional stiffness and to offer a frequency response above 1 kHz. Strains are too small, at most a few parts of thousands, to be measured directly, so workarounds must be established, including flex structures and 4 gauges being arranged in a Wheatstone bridge circuit. Slip rings or local telemetry are required to feed a continuous current to the gauges and acquire the signal from the bridge circuit. The use of slip rings can act to limit the maximum RPM of the shaft, and wear can significantly reduce system reliability. The use of local wireless telemetry can limit the maximum bandwidth of the system and can either be prone to signal dropout or create significant electromagnetic emissions that may interfere with other sensors, electronics, and telemetry on the vehicle. Strain gauge sensors are typically not robust or resilient to harsh environments and are susceptible to interference from background electromagnetic radiation and magnetic fields. Displacement sensors. This method typically uses a pair of identical tooth discs attached at opposite ends of a portion of a shaft, which enables a twist angle to be determined from the phase difference between them through an optical or magnetic measurement. This in turn enables torque to be calculated. The main advantage is the ability to overload the sensor to the maximum load capacity of the twist shaft. Disadvantages of this method include: it requires the shaft to be rotating, so cannot measure static torque or load. It requires a reduced diameter section of the shaft, known as a torsion bar, to enhance the twist angle, which can have a negative effect on the mechanical stability of the system. Relatively bulky measurement rings or collars are required to be attached to the shaft. It is also sensitive to temperature. Magnetoelastic sensors. This method for torque measurement uses changes in magnetic permeability that occur on regions of a special shaft surface because of torsional stress from the applied torque. These variations in permeability are measured by encircling the shaft in some pattern of coils of wire and observing differences in induced voltages. The main advantage is it is more robust than strain gauges and does not require a torsion bar like a displacement sensor. However, there are significant disadvantages. Permeability does not depend exclusively on torque and will vary with frequency, temperature, and magnetization. Permeability is neither an intrinsic property of the magnetic material nor a single-valued structure-sensitive property. Local variations in magnetic properties of a typical shaft surface limit the attainable accuracy. Calibrated electronics are specific to each calibrated shaft and sensitive to variations of the gap between the shaft and the pickup coils. Impact to the shaft can disrupt the magnetic properties on which the calibration is based. The technology is limited to the instrumentation of components manufactured from steel, and it is susceptible to the interference of stray magnetic fields. Transense SAW technology. A wireless, passive, non-contact sensing system consisting of 2 main components: the SAW sensing elements connected to a close-coupled antenna mounted to the shaft, and an electronic interrogation unit called a reader connected to its antenna off the shaft. The reader sends an interrogation signal which is picked up by the sensor's antenna. The sensing element does not contain any DC power source and works as a passive backscatterer, reflecting the interrogation signal back to the reader. The backscattered signal is affected by strain and temperature by a known amount. The reader analyzes the received backscattered signal and calculates the value of the measurement. The advantages of this approach are an immunity from background interference. completely wireless installation with small, light and passive components only on the shaft, very high-speed measurement of the physical property, there is no torsion bar required and so it works on a stiff shaft, compact dimensions that can be easily packaged into a complex system, and it provides an additional temperature signal. The disadvantages of this technology are it is not available as an off-the-shelf sensor and it must be designed into a system, and it requires proprietary Transense SAW devices and ASICs. To find out more about how Transense can help you, contact us today.